We call this workshop Aguante Rust. We use the word in Spanish because I couldn't find a good translation to English. For those speaking French, that could be Allez Allez Rust, but I don't know if you want to suggest a translation in English. Okay, this workshop will be mostly the first time will be an introduction to the language for those who hasn't used Rust in the past. We were talking about the fundamentals of Rust, syntax, some about the organization of the code in modules, how to write tests, how to organize the test. And I think that the hardest part is or the most important and interesting part of Rust is the ownership, the concept of memory management. So we will be talking about that, ownership, lifetimes, and a little bit about traits and genericity, generics. So that's the agenda for today. As we said, I prefer you to interrupt me at any moment. Feel free to ask questions. I don't want this to be a monologue. It's better if we interact during the talks. I have these slides, and I also have some examples of code that I will show you afterwards. Any questions so far? Ideas? Okay. Cool. Okay. The first question is why Rust and what is Rust? Or why do we use Rust for this kind of things? And Rust has some goals. Rust excels in some type of software. The main benefits of the idea of Rust is the speed, the security, and concurrency. If you go to the main website, you will find these words, these words in big size. The idea is Rust adheres to the principle of zero-cost abstractions, which means that the code you write in your program is the code that will be executed, and no more than that. The compiler won't add more instructions than the ones you added, but technically, except for a minimal runtime that it's added at the beginning of the execution of the program, but no more than that. That's the principle of zero-cost abstraction, like other languages like C or C++, that also adheres to this principle. The main goal of the innovation of Rust is the usage of the memory. I think the administration of the memory. Rust wants the memory to be used in a secure way. So that's the hardest part, I think, of writing a Rust program. We will be talking about that later. And another goal is to make writing concurrent programs easily. They say fearless concurrency. They provide tools for concurrent programming in the standard library. So you can find some other words that are funny in the website. They want to empower everyone to write good software. The software is extremely fast. And other important thing is that they assure backward compatibility. That means that there is a 1.0 version or 1.x version of the Rust compiler, but there won't be a 2.x version of the compiler being incompatible with the 1.x. You can compile an old program with a newer version of the compiler, and they assure that it will continue being like this. Rust is mostly a low-level programming language. That means that you have the control or the power on how data is allocated, how data is created and destroyed, and low-level instructions, but it has an API or an interface of a higher level. You have tools for abstractions like in higher level programming languages. It was they call ergonomic tools for the developer. In the sense of the security or safety using memory, Rust prevents accessing invalid data or invalid memory, and it does it at compilation time. So it has not runtime cost in the runtime of our program, which is very good. It prevents, for example, buffer overflows. You know what a buffer overflow is? Yes. Okay. 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 Which prevents most of memory errors and many security problems in software. For example, the majority of modern bugs are related to this kind of problems. In Rust, there are no dangling pointers. That means that if you have a pointer to a memory area, that pointer or that variable containing the pointer is always valid. You can use it. The compiler allows us to use it without any problem. If there is no valid data, the compiler won't compile our program because invalid references are discarded, and this variable will be marked as invalid, and we won't be able to use that variable in our program, that reference in our program. Another good thing is that these rules prevents race conditions on the data when we use concurrency. That means data races. In Rust, there is no using the standard array and using safe Rust. We cannot write to the data race. Okay, and I think that all of this makes help us writing software that has a good quality, which is the maintenance. I think that software written in Rust is more maintainable than in other languages, at least other languages I've used. Because the compiler has many helps, many aids for the developer. The error reporting is very good and very helpful. Okay. Rust has many tools in the family. The main tool is the compiler itself, which is called rustc. And there is another tool which is called Cargo. Cargo is the part of the ecosystem of Rust, which will be interacting with. And Cargo will help us to build our project. For those having experience with C, Cargo is similar to Make in that sense. Yes, for building a Makefile. But not only that, Cargo manages the dependencies, external dependencies of our code, of our project. For example, like, I don't know if you have used JavaScript, but like npm, for example. So some commands quickly to create a new project. We use cargo new. If we have an existing directory, we can use cargo init. To compile the project, we use cargo build. To compile the project in release mode, cargo build -- release, which does more optimizations in the compilation processes. To run the program directly using cargo, we can write cargo run. To run the test, cargo test. To generate the documentation with the cargo can generate a kind of book in HTML format to be able to be accessible with the browser with cargo doc. There is a syntax to write that kind of documentation. If we are developing and we want just to check this, the syntax is correct, we can use cargo check. And to format the code, we use cargo FMT. There's a tool called format, which applies all the rules of formatting to format our code. For example, the amount of spaces, indentation. If the line is too long, it breaks in a few lines and things like that. And there is a very good linter, which is part of the project called Clippy. Sorry, this is wrong. It's cargo Clippy, not Clippy cargo. You run it with cargo Clippy, and it will give us some warnings about more like stylish warnings, which will help us to improve our code performance or usage of variables or the usage of methods of the standard library and so on. There are some alias. For example, for cargo check, you can write cargo C. You don't need to write check. For example, cargo test, cargo T, cargo run, cargo error, cargo build, cargo B. Okay. We'll talk about the syntax a little bit. Cargo is Rust is a strongly typed language. That means that the variables have types. The types are well defined. We define a variable with its type. There are main types. For the numerical types, we have the version with sign and version unsigned. The integer of 8 bits, 16 bits, 32 bits, 64 bits, and the unsigned version. We have the floating point, that data type, 32 bits and 64. It's like the float and double of C. And there is the version U size and I size. The version that takes the amount of the length of the word of our architecture. For example, if we are compiling a machine of 32 bits, U size will be 32 bits long. The bool type for true or false options, and the char is quite different from C. In C language, a char is just a byte. In Rust, a char is it's a bit tricky because a char in Rust represents a character of UTF-8 encoding, so we can hold any character of UTF standard, like an emoji, for example. So it's not common use. Char is not common use in Rust like it is in C. If you want to represent a byte in Rust, you use an U8. We can have arrays of fixed size with this syntax. For example, it's an array of 3 elements, 3 to 8, 2 plus. We can have an aggregation. We can of different variables of different data type, and we have dynamic types, which are located in the heap of the memory. The vector, the string, hash map, etc. A question: do you know what the heap and the stack are? Everybody knows what's the heap?
Yes.
And stack? Okay, perfect. Good. Okay. Variables are immutable by default. We use let to define a variable, to declare a variable, let equals true. So Rust is a strongly typed language, but the type can be inferred from this declaration. So in this case, T is a bool. To make the variable immutable, we use mut. Here we are declaring a variable which is a tuple of two U2 variables. We can reuse the name of the variable, redeclaring the same name, but we don't recommend you use this practice because it could be confusing on the source code. If you have let t equals true, and then afterwards you put let t equals 42, it discards the previous value and it's a new variable which has nothing to do with the previous value. Okay? It's not that the content of the variable changed. No, it's a new variable. So for example, in this function, let v equals return integer, v has the type I32 because it's inferred from the return type of the function. For functions, this is the syntax. We have this arrow with the return type. The return type could be any type. And one thing in Rust is that the return value is the last line of our function, and we don't use the return keyword, and we don't put the semicolon at the end of that line. Yes, for example, here a plus 1 is the last line of our function. We don't use return, I will put the semicolon. If we want to have an early return of the function, yes, we put return and the whole sentence, whole instruction. Okay, one of the first-class citizens of Rust are the structs. The structs are complex data type. A struct is a set of elements are put together and are component. They have a name, and they are treated as a unit. And structs can have methods. So Rust is not an object-oriented language. There are no classes and there are no objects, but there are structs. So that means there are no properties of object-oriented languages. There are no inheritance, and there are no this kind of polyformies that you can find in other languages. For example, this is the syntax of structs. We can have different kinds of structs. The first variant is the most common. You have a struct, for example, struct person, and you have the fields. The fields and the type of the field. Yeah, is the most common form. The second form are the tuple structs. You have the name of the struct and the components or the fields of this struct are not named. They are a tuple, and the syntax is just the syntax of the tuple. In this case, we have a tuple of only one element, for example. Yes, the tuple can hold one or more elements. For example, we have the struct Celsius holding a float of 32 bits, and we have the struct Fahrenheit holding a float of 32 bits as well. So what's the goal of this? Why do I want to have these two structs? Anyone wants to answer that? Yeah.
It's like an alias, right?
Sorry.
So someone saying something. I guess someone will be able to like define some methods on them, or rather maybe traits if
Yeah.
we have it as a structure.
You can define methods on these structs, and you cannot define new methods on a float 32, for example. But more than that, more than defining methods, you can have this, for example. You can have this function convert to Fahrenheit that accepts Celsius. And you are sure that you will call this function only with a Celsius struct and not with a Fahrenheit or not with any other float 32. Because the Celsius and the Fahrenheit are different data types, even if internally they are exactly, or they are represented in the same way in the memory. Okay. And the last type of structs are the unit type. Unit type in Rust is like the void in C language. It's a type containing nothing inside. It's just like a label. For example, struct something. You can use it to define methods, for example, or to define or you can get a unit type, the struct, just to represent that, to represent something. The other important data type is the enum. The enum, it's a data type that has different values, and the value of the variable can be just one of these choices, and only one of them. That's an enum. And there are different variants of enums. The more common is to have an enumeration of items. For example, we want to represent cards. We have the suite for the card. So the enum suite is declared as this enum with spades, hearts, diamonds, and clubs. And I declare a variable suite of type suite, and I assign the value suite spade. Yes, I can assign only one variable of the enum to that variable. That's the most common type of the enum, but Rust also have this interesting enums called tagged unions. Tagged unions are unions that has labels, and they can have other data types inside every choice. For example, I want to represent a full card, not just the suite. So a card could be a joker, could be an spade, but if it's an spade, it has a number. So the spade holds a U8, and the club holds a U8, and the diamond holds a U8, and the heart has a U8 inside. So I can declare a variable, my card of type card, and I assign it the variable card diamond with the number 9 inside. And I can declare my joker, and my joker is a card, and I assign it a card joker, a variant of the enum. So different values of this enum have the different data type. And the last type of enum is the enum with a struct inside. Instead of having a tuple, we can have structs in some choices, for example. The card can have, for example, I can declare this enum play. One type is card. In a play, I can put a card on the table, or I can pass. If it's a card, I represent it with the suit and the number, so it's unstruct. If I pass, there's no more information. So this is like the tuple struct, but with an struct. Okay. Rust has two interesting data types. They are used everywhere in the standard library. The first of them is the option. The option is a generic type, and option is used to represent a variable that can contain some value or nothing. In Rust, we don't use the null pointer. When you have this situation, you use an option of something. For example, an option of a float, like this function. So the option is, in fact, an enum with two choices, some and none. Yes, somebody wants to. Somebody raise
Yeah.
their hand.
So actually, this is very similar to have something called maybe. So you can you hear me? It's okay? No?
Again, please.
Can you hear me very well? My mic is having trouble.
Now, yes, I think that now it's better.
Okay, so I'm guessing this I think is very similar to Haskell, right? Because there's some kind of maybe data type that is this is maybe to catch errors, because you don't have try catch also in Rust, right?
You don't have try catch in Rust.
Yeah, so you use this for that maybe, right?
You use for the maybe data type. Yes.
Yeah. Okay.
Yes. Perfect. It's like the maybe. In Rust, we use the option. We do match for that. Yes. We use the match for the data type. We will see some examples. So the option is generic because the data type of the sum variant is defined at compilation time. Is the type T. So it can be anything. Okay, so for in this function, If then equals 0, I return none. Okay, so I return sum with the division of the numbers. The other data type, which is very used, is the result. The result is used to represent a value or an error, something that can be a value or an error. So it's used everywhere in the standard library in input-output operations. For example, in the file read, file open, or operations like that, you will see that they return a result instead of the value itself. Because in Rust, we don't have the try catch, we don't have exceptions. The way to indicate that there was an error is with the result. So the result is also a generic, but it's a generic with two generic types. One for the OK version and another generic type for the error version. So the result is an enum with two variants, the OK and the error. Yeah. And it's used, for example, accessing files. We have this function count lines, and it can return a result because there could be an error accessing to the file. Okay. There are some useful operators. We can do pattern matching, but both option and result have many methods. One of the most used methods are the operator, the question mark. The question mark is very interesting because it can be used for the option and for the result. If you have a value, for example, which is an option, and you have this value inside a function, and the function returns an option of the same type, we can use this question mark, and if the value holds the non-version, this question mark will return the function with the non-version, with the non. And if the value holds the sum version with a value inside, the question mark doesn't return the function, but give us the content of the sum. And the same for the result. If it's okay, the question mark give us the value which is inside the okay variant. Okay. Give you a second, please. Sorry. There are many methods. The unwrap methods, it's kind of dangerous. I recommend you to avoid it. You should treat errors in a good way. Unwrap give us the value inside the OK version of the result or inside the sum version of the option. But in case the value has is an error or a none in case of the option, the unwrap method will panic our program, which means that it will abort the execution of the program immediately. So that's not a good way to handle errors. There's another version of unwrap, which is unwrap or. With unwrap or, we can put a value in this argument, indicating that this is the default value. If we apply the unwrap or method to an option, and the value is unknown, the unwrap or method will take the value we provided in this function. Yes, it's like we are providing a default value with this invocation. For example, if you have a, yes.
So is unwrap or function is a way to handle unwrap function, a failure of unwrap function?
It's not a way to handle errors. It's if we have a default value for some situation, we can use unwrap or. But if it's not the case, we cannot use unwrap or. For example, suppose that we have a configuration file with many variables inside the configuration file. And what if the user didn't provide us one of these variables in the configuration file? Okay, if we have a default value for that variable that wasn't provided, we can use a default value. But if we really need that value, we cannot use a wrapper. We don't have a default value. So we should inform the user that that value should be provided. Is it okay? Does it make sense? Okay. The expect method is similar to unwrap, but you can put a message inside. This message will be displayed in the case of a panic, displayed in the standard error output, the console of our execution. So I say you that we should avoid using unwrap and expect. And you can there are some which can be useful, like isSum. isSum, we can use isSum to ask to check if the variable holds a sum or is none, is okay for the result or is error. So they return a true or false. We're going to use them inside an if condition, for example. But in Rust, we use pattern matching a lot. Rust has a very good pattern matching operation. It's more powerful than in C. Maybe you have used pattern matching in Haskell or in other languages. Rust has some similarities with Haskell in this sense, for example. And this pattern matching executes the first branch that meets the condition. For example, if I have the enum card that I showed previously, I can use match with my variable, my card, and I can put this condition card diamond with a value inside, and this branch will be executed in the case my card was a diamond variant of the enum. So in this branch of the match, I will have the value variable created, declared, that was the value inside the enum, and I can use this variable value for everything inside the branch of the match. In this case, I am printing out the value in the console. With the match, we must declare all the possible all the possibilities, all the possible choices. So with an enum, we have some variants, and we should write all the variants. If we don't want to distinguish among them, we can use this underscore, and it's like the otherwise or the else in other languages, because I don't want to distinguish the other cases, for example. I just wanted the diamonds in this example.
Just before going, I have a question there. See, for example, you say print line, right? There's a comma. There's the anything match, right? And what if I want to do a lot of lines there? Do I use a semicolon or something?
No. You use the brace. This you just use the brace. The comma is used to separate different branches of the match. But
let's say that I want to print two things, for example, for the diamonds value option, right?
Yeah, you put these the two lines inside the braces.
Which braces? Ah, okay. I got it. Yeah. Ah, okay. Yeah.
Maybe I can write in the chat.
I understand. Yeah.
Okay. You put the print like this. Okay. Cool. And the match can be more complex. To test all of the possible values. So look at this example. I have a tuple composed by 3 I32 items, and I match. This is a point, for example. I am modeling a point in the space, the three-dimensional space. I match a point, and the first branch is I put 0 for the x for the first value of the tuple, and I use y and z. So I mean that this branch will be executed only if the first element is 0, and I accept any value in the y and the z. The second condition I put is give me anything in the first value, but I want the second value to be 0, and give me anything in the last value of the tuple. Okay, I use the underscore when I don't want to use the value inside the branch of the match. If I wanted to use the first value, I should have put an X, for example, instead of the underscore. And since I should check for all the possibilities, I put the underscore without the tuple, because this underscore means everything else, and I don't do anything in here. There's a simple variant of the match, which is the if-let. If-let, you should think the if-let as a little version of the little brother of the match. Test only for one possibility. Difference between using y and z and underscore, can we use interchangeably? If we don't want to use the value inside the execution of the branch, we use the underscore. Like in the second branch, for example. The second branch, I am not printing the content of the value, so I put the underscores. That's the question. Is that the question? Okay, perfect. With if let, we check for just one condition, just one possibility on an enum. Remember that the option is an enum. So we can use if let for this enum. We can use if let for my card enum. In this case, I am checking for the option and I am using the sum and the I. This means that if the value holds a sum, which is the case of this number, this branch, this if, the content of the if will be executed, and we will have the value, the variable I with the value that was inside the sum. Okay. I could have used the if let in the previous slide. For example, I could have put if let card diamonds value equals my card, for example, instead of using a match, because I just wanted only one branch and not all the possibilities in this case, in this particular case. Okay. Of course, with if let, we can use the else, which doesn't give us a value or a variable inside, but it's executed in the other situations. Loops in Rust. Rust has the loop keyword to indicate an infinite loop. This loop will run forever. For example, look at this. I have a variable called count. I add 1 to this count on every round. For example, I can put this if, the normal if, checking the condition that count equals 3. And if that's the case, I continue. Continue, we'll go to the top of the loop and start the next round. And I can use break, for example. In this case, I have this other if, checking the condition that the count equals this other number. And arriving that, I break the loop. So I exit the loop. Okay. So loop is used for infinite loops. For normal loops, we have the for, which is very similar to the for in Python, for example. For iterates over an iterator. So for example, in this case, we are iterating over an iterator of numbers. This is a range 1.101. A range of the numbers starting from 1 until 101 exclusive. So until 100. And inside the for, you can do whatever you want with the variable n. Okay. For is mostly used with iterators. For example, we have a vector. We can iterate over the values of the vector with a for, like this, for name in names.iter, and names.iter give us each value of the vector each time is invoked. So inside the for, we have the name variable. This vec with the exclamation mark, it's a macro that construct the vector and inserts these values after a construction. Why? Yeah, Marcos.
you know, that's something that still confuses me about Rust, right? These names that have an exclamation point, those are macros, right?
Yeah.
And you can see that you have name is an iterator, right? And you put print line, exclamation, and name, right? So name's not actually, so name is not a variable, so it has something else inside, right? But it knows that it has to take the value of the name, right? Right?
Yeah.
Because the iterator has something else besides only the value, right?
Yeah, but name is just a value. Name is a string.
Okay, but see, because in my head, since it says that it's an iterator, it needs to somehow remember, or somehow it remembers where was the point in the names vector, where it is, right?
Yeah, the iterator remembers that. That's true, but the for loop is controlling that. The for gives us the name variable, which is just a string. It's no more than a string.
Okay. Okay. Yeah.
But names is a vector of strings. Why this is a macro? Because in Rust is a strongly typed language, so functions in Rust should receive must receive a well-known data type. In this case, vec being a macro can receive any data type we want. In this case, we are providing a set of strings, but we can construct a vector of integers, or a vector of floats, or a vector of anything else. And that's the power of macros. It's the reason we need a macro for this. Okay. The while loop, it's like in another language. While receives a condition that must test to a boolean, to true or to false, and while loops as long as the condition is true. While let is the version, is the loop version of the if let. It's similar to if let, but inside a while. So with while let, we test for a variant of an enum inside a loop. In this case, while let sum I equals optional. I have a variable called optional. We can be sum 42, or we can be none, for example. So while let will loop as long as the optional is sum. If inside the code of the while let we change the content of optional to none, this will let won't be executed anymore. Will stop executing. Okay? Is it clear? Cool. Yes. Okay, let's move on. We said that in Rust we have classes, we have objects, but we have structs and enums with methods. So how we define methods? With the impl keyword. So we have our struct person, for example, and afterwards we use impl person. So impl the name of the struct, or impl the name of the enum, and then we put functions inside this code, this block inside the impl, and these are the methods of the struct. If we want to receive a reference to the variable, the object person, we use the ampersand self. Ampersand self is holding a reference to the struct used to invoke the methods. For example, let name equals okay, point full name. And here we are referencing the person, this particular person. Okay. So we define method for the structs this way. If we don't want to have this reference to the struct, it's just a general function or a general method. They are called associative functions, and they are used mostly to construct the object, to construct the struct. There is a convention that the constructor is called new in Rust. So new doesn't receive a person. It returns a person. So it's an associative function because it doesn't receive the self in any way. So new receives the first name, the last name, and give us the person. Okay, the person is constructed this way. The name of the struct and all the elements of the struct with the value. And the way we call it is person, this points, and new with the arguments. Okay. So this way we define functions, methods, or associative functions to structs or to enums. Okay, let's move to traits. Traits in Rust. Traits are like interfaces in other languages, like in Java, for example. And traits are meant to define common behavior for structs or for enums, similar to other languages. It's a kind of polymorphism in Rust. We can abstract behavior with traits. For example, we use traits to represent a capability. It's something that this data type can do. How we declare a trait? We use the keyword trait. We put a name for the trait, in this case, full name. And we put the declaration, just the declarations of the functions of this trait inside the block. So this trait called full name has a function or a method called full name, receiving a reference to the self and returning a string. It's just a declaration. And we put a semicolon at the end of the line. This trait has only one function, only one method, but it can be any method as we want. So in our code or in the definition of our person struct, we use impl, but in this case, impl and the name of the trait. For example, impl full name for person. So we can have the implementation of the trait full name for person, the implementation of full name for animals, or for whatever we want. Okay, questions, comments? No? So we can use traits with one type of genericity. We can, I don't get the ampersand self-reference. Yes, or maybe we will explain the references a bit later when we talk about the lifetimes and ownership. Is it okay if we talk about references later? Yeah. Okay. Perfect. we can use traits with generics. We can use traits with for a type of polymorphism. Polymorphism Rust can be done in different ways. For example, we can define a function receiving not just a concrete type, but a data type that we don't want, that we don't know what data type is, but we want this type to implement a trait, to implement some methods. For example, look at this function, showName. ShowName receives the things in the parentheses. It's a variable called v, implementing of this abstract type double v. And double v is declared inside this name of the function with this notation, with the angle brackets, saying that implements a full name trait. And full name was the one of the previous slides, this one. What's the difference between WV and V? Okay, in this case, V is the name of the variable we will have inside the code of the block, the code of our function. And WV is just a link in the declaration of the function that help us to specify the type of this variable V. It's not a variable. It's a type, an abstract type, which is defined in this function inside the angle brackets. So WB is a trait full name. It's something implementing a trait full name. So traits are essentially type classes, right? Yes, we can say that. Traits are kind of type classes. Yeah. Or are similar to that classes. So we don't know what V is, but we are sure that V implements full name methods. So inside the code of the function, we can call the method of this trait. Okay. So our name is a function, implements full name trait. No. ShowName is not a function implementing the trait. ShowName is a function that receives a variable, an argument v, and this argument v implements the full name trait. Okay. There are many traits already defined in the standard library. What does it mean I implement the default for what? Okay, I am moving to the default trait. Let's go to the default trait. There are many traits already defined, already declared in the standard library of Rust. They are called utility traits. We can implement that utility traits in our own data types, in our own structs. For example, the default trait. Default is a trait having just one method, call it default. And the idea of default is we create a value of this data type just with default values. not specifying any initial value, just the default values. For example, I can implement the default trait of the standard library of Rust like this: impl std default for person, and I must implement the default method, and the default method returns an instance of person, of the struct person. So I must create a person inside this function. What if the default and debug both implement the method print? What is the resolution order? Oh. We should avoid having this kind of conflicts. But there's a resolution order. If both of them implements the there's not an order. If we want to have this, we should call the method with the name of the trait to specify which of the method we want to call. So we will be calling the method with the name of the trait and then the name of the method. I can look for examples afterwards to send you if you want to have this, but we should avoid having the same name of the method in different traits. Okay, so the default to create a new element with default values. I can implement this function the way I want. Okay. For example, in this case, I could have put some names inside this implementation of the function just to have initial names. If I want to use the default implementation of default, I can just put this annotation. In Rust, this is called an annotation. It's a kind of macro, and the compiler will put the code of these functions automatically. This annotation for default will put the default method with default values for every element of my struct. Okay. If all the elements of the struct implements the default trait, I can use default for the whole struct. It's the same for debug. Debug is meant to be used for printing the content of the data type in a debug way. Another interesting utility trait, which is defined in the standard library, is from and the trait into. From and into are the idiomatic way to implement a conversion between types, between data types. So with from, we can define a function, we can write a function with the implementation of the conversion from one type to my type. For example, in this case, I want to convert from a string to my person struct, my struct person. So the trait from is also a generic because we specify this with a data type. So we put the impl from with the concrete type inside the angle brackets, in this case string, for person. It's different that in the previous case, we put the input without any angle brackets because default is not a generic trait. So we must implement the from method inside this block. And now the from method receives a value called S or whatever you want, but the type of this S is a string because we defined this inside the angle brackets. And it returns a person, a new person created. So this could be a parser, for example, for a string. Suppose that you serialize the elements of the person in a string. We can call it with the from method, for example. So from is used as an idiomatic way for converting data types. If we implement from, the trait into is from is preferred instead of into. Okay. We'll talk about the code organization in modules and tests, and then we will do a break to grab a coffee. Okay, we can divide our code in Rust in a project in modules. Modules are like namespaces in other languages, like in C++. And we can have modules in the same file, to have namespaces in the same file. For example, look at this example. I have my main file, main rs, and I have this mod keyword, mod greetings, and I have functions inside my mod greetings, my module. For example, this function, hello, printing hello world. By default, functions inside modules are private. So if I want this function to be called from outside the module, I put the pub for public keyword at the beginning of the function. So in my main function, I just give all the path to the function I want to call. Greetings, points, hello. So I just give all the path, the complete path, the complete module's path to my function. I can use self to refer to the same module, and I can use the super keyword to refer the parent module. For example, if I am inside this greetings module and I want to call a function which is in the parent module of greetings, I can use super points and the name of the function. It's just the point in the console. Okay, Gabriela. Thank you. Questions? Any questions so far for modules? No? It's okay? Okay. We can have modules in another file. For example, I have my main file. Yes.
So sorry, it come to my mind later. When we use 2 points, 2 columns, we can use it for struct functions and also for modules, right?
Yeah. Yeah. It's used for functions of structs, and it's used for the variant of the enum, as we saw before, and it's used for the path of the module.
So let's say, unfortunately, we have the same name for a struct and a module. Like we named our struct, but a module external module is used, but it unfortunately had the same name of our struct. So,
okay.
Am I just pushing too hard?
Yeah. Okay. The convention is that the names of the structs should be capitalized like that. Like in, how do you say, in camel case, with words with capital letter at the beginning, camel case. In this case, person with the capital P. And modules are written in lowercase. All the name of the module is lowercase. In snake case instead of camel case. If you have more than one word, we separate them with an underscore. Okay. You can disambiguate these kind of ambiguities. You have the grade modifier, for example. Grade. So you refer to the person in the root of my grade and not an external person. Okay, Marcos.
Right, right now I'm using mod, right, to call the models I create inside. It always looks for for example, greeting.rs or greetings directory inside mod.rs, right? And what is the difference between a crate and a model? You use for a crate, right? And then there is extern crate. So if I'm going to use some crate, it has to be inside these. There is this repository of crates in the right, called crates.io, I think, right? Or not?
Yes.
My question is, you have to use mod for the models you create inside your directory, right? You use keyword when there's something else in the internet, right?
No. Not only something else in the internet. The use keyword is like the alias.
Okay.
The use keyword is just I can use for replacing all this whole path for this name.
Okay.
Not only for external crates.
Okay.
In this example, in my previous example, I have no external crates. It's just one file with a mode inside, a mode block inside my main rs, and I can put mod greetings hello on top of the main function, and that means that hello keyword, hello word refers to greetings hello. It's just the replacement of all this path to the word hello. It could be an external path or an internal path. Use is like this. It's not the import of Python. It's more than an alias than the import of Python.
Okay. So extern crate. What is extern crate then? Use extern crate, right?
Okay. As Daniel said here, extern crate is not used anymore. It's an old standard, and the new version of Rust, we don't use extern crate anymore. We just use the use keyword with the name of the external crate at the beginning. If we want to disambiguate, we use, for example, suppose we have an external crate called Lambda works. We use Lambda works sum. And I am using the sum function of Lambda works. It doesn't exist, but it's an example. If I want to refer to the sum function of my own crate at the top of my crate, I can use crate sum. If I put both of these sentences, it won't compile because I am defining the sum name twice. It's not possible.
So essentially, use is just for an alias then, because this still
use is like, just an alias.
It's a model.
Yes, it's an alias. I can write without use. I can write my whole program without using use. It's just an alias. It's not an import, it's an alias. Yes, an extern crate is an old standard. We don't use extern crate anymore. Since 2019, I think. 5 years ago. Let me show this other example to see if it's clearer. If I have two files, the main rs and greetings rs on the same directory of my project, I refer the second file, greetings rs, putting this mod greetings, which we'll find at the first inside the same file as in the previous slide. But in my own file, I am not having this greeting module. So it will look for the greetings rs file. Okay, so it's the same as in the previous version, but in a different file. In the previous version, I have the module in the same file. The second version, I have the module in a different file, and with mod, I am importing the module to the main rs. Okay, both versions are identical, are two ways for doing the same thing. The second form, I am separating in two files, two different files. If I want to have separation in directories, in subdirectories, it's a bit tricky. I have to put files inside directory. In this case, for example, I use the phrases directory or subdirectory. And in the main rs, I import the module phrases with mod phrases. And inside the phrases directory, I should put a mod rs file importing all the modules of this directory. For example, I have the greetings rs file. So in the phrases directory, I have the mod rs file with this mod greetings. And as I wanted to have this greetings module be called from outside phrases directory, I have to use the pub to make it public. Pub mod greetings. So in the main file, in the main function of the main file, I call the function, giving all the whole path. For example, phrases, greetings, hello. This is the whole path for the hello function, because I should enter the phrases module, which is in here, and then inside the phrases module, I have the greetings module, and in the greetings module, I have the hello function. I could have used the use keyword just as an alias, and no more than alias. I could have put use phrases, greetings, hello, and then with this declaration, I just put hello on my code and not the whole path to the hello function. Is it okay, Marcos? The rest?
Yeah, great.
Okay. Questions so far? Anybody? No? Okay. How do we use external crates? You know that in Rust, the external libraries, our dependencies are called crates. And there is a common repository in the crates.io website. Crates.io. Crates.io. So we can use the crates, define it on that, or upload it to that repository. It's a public repository. So our project, our Rust project is composed by many files. The declaration of the properties of our project is in the cargo.toml file. It's a kind of configuration file of our project. In this configuration file, we have a label called dependencies. And under this label, we put the name of the crate and the version, for example. And this will tell cargo to look for this crate called log in crates.io, in the crates.io repository, on the crates.io website. So in our code, we can use the use to define the alias. And for example, use log ... info, and I have the info macro in my code, for example, ready to use my code. Dependencies by default are searched in the crates.io repo, which is the official Rust repo, but we can import dependencies from a GitHub repo, for example. There is a syntax in the cargo toml to include a dependency from a GitHub repo. I think that in Lambda works is done like that. If you go to
Pablo,
Yeah.
I actually just yesterday learned to do this, right? So what I did was to clone a GitHub repo, and then I added path, right, in the dependencies. So he can take the clone directory, right? And I had a problem with Lambda works because inside Lambda works you have like a crypto directory and you have like math directory, and those are packages. But if I gave it the path to just Lambda works, there's something called an what's the word? An environment or something. What is that? You have the package and you have this environment, right? Or something else. I had to check the name.
Yes.
Question is, what is the difference there? Let me check.
Okay. Proto said, I always struggle reading the docs from crates. It's a game of trick, or I just need to get used to it. No, there's no trick. You need to get used to it. At the beginning, I was struggling reading that docs as well, but nowadays I like the docs, Rust docs.
So that is workspace and package. I know what package is. What is workspace? How do you use it? Right?
Okay. First, look at this.
Mm.
You have this internal crate of LambdaWorks called Crypto. Crypto is a crate inside Lambda works, and the cargo toml file contains the definition and the configuration of this. And you look at the line 10, you have the dependencies. You have the crates, the external crates included, used by this crypto crate. For example, Third or SHA-2, SHA-3. They are crates that are uploaded in crates.io. Okay. What's a workspace? A workspace is an aggregation of internal crates. You can divide a bigger project in smaller projects or sub-projects, and the definition of the big project is a workspace. So in a workspace, you declare the components of your project. For example, the cargo toml of the main directory of LambdaWorks is this, and in that cargo toml file, you define the components of this workspace. For example, LambdaWorks crypto, and it's a crate in this path. LambdaWorks GPU, LambdaWorks math is in this other path. Okay. So they are independent crates, but all of them are on the same family. So we continue. We'll talk a little bit about testing and how tests are written in Rust. How we write test functions. What's a testing function? Tests are functions in Rust that verify that the rest of the code is working as expected. That's the idea of writing test functions in general. How is the body of a test function? We have a first part with the setup of the data and the state necessary for the test. And then with that data, we run the code we want to test. We give some results. And we affirm the expected results. We use assertions to compare the result given with the expected result. Test functions are identified with this other annotation. This annotation starting with this operator. We put this annotation in the line before the declaration of a function. And for the assertions, we use the assert macro. Again, this is a macro because we can make assertions for different data types. So it's a flexible macro. We have a family of assert macros, not only assert, but we have assert equals, other variants of this assert. For example, we can assert that the person.age is greater than 18. This inside a test, if it's true, the test will be okay, test will pass, and if it is false, the test will panic, and the compiler will tell us that the test failed. Okay? So test functions are only compiled when we run cargo test. So to do that, we should put the test inside a module that will be compiled only on that situation, on that case, on the invocation of cargo with test. So we declare a module test. This is a regular module. So it can have any name. So I put test in here for the name of the module. And I want this module to be compiled and to be included in the compilation only when I run cargo test. So I use this other annotation, CFG test, which tells the compiler to include this module, this piece of code, only on test invocation. This mode could be on the same file, but could be in a different file as well, as we saw before. Yeah, could be on the test rs file, for example. For unit tests, we put the test functions in the same file at the bottom of the file. Unit tests are meant to test the behavior of single functions in our code. Okay. So in Rust, it's common to put the unit test on the same file of the methods, for example, of our struct at the bottom of the file. And then we have integration tests. Integration tests are tests that are meant to test our crate, our code as a whole, not as a individual unit. We use our crate, our module, yes, our whole crate as a user of our crate. For example, we use Lambda works the same way as a user of our Lambda works will do. And integration tests are placed in a special directory called tests next to the source directory of our code. Okay, it should be, it's a convention, it should be on this specific directory. Each file inside this test directory is compiled as a separate crate. So each file must include our code, the code we are testing, our crate, as if it is an external crate. Okay, with the same syntax that we saw before. I go back. The same syntax as this, for example. Use log .info. We will put here the name of our crate, for example, Lambda works crypto in the integration test. One thing, a little detail of integration test is that they cannot test functions in the main rs file. So in Rust, we have two different kinds of crates. the binary crates and library crates. Binary crates are the programs that are compiled to an executable, and they have a main rs file which contains the main function, like in C, for example. And the library crates are not meant to be compiled as a binary crate. They are included in our crates, like Lambda works, for example. Lambda works crypto, for example. So we put the root of this library crates is a file called librs instead of main rs. So we can do integration tests for binary crates as well, but not for the functions inside the main rs file. Okay. Is it clear? Questions? Yes. Yes? Okay. Okay, let's move on. We will start with a different subject. We will talk about ownership and then lifetimes. This is a huge subject. It's important to understand this subject because it's what makes Rust mostly hard. It makes Rust different than in other languages. Okay, so what's the motivation of ownership? The idea of this part of the language, this part of the compiler, is to eliminate the possibility of some kind of bugs in our software. A category of bugs. Which bugs? Some bugs of memory management. The bugs derive from the presence of null pointers. The bugs that occur when we use memory after we release a variable. The double release. If you have used C, for example, C language, if you write free twice, it's an error, it's a segmentation fault in Linux. Buffer overrun, for example, getting a value in a position that it's higher than the size of an array or a vector. Iterator invalidation, and data races, race conditions in accessing data. How does Rust achieve this? By restricting the program that are considered valid. So in Rust, we don't have as much freedom as in C, for example, because the compiler will be restricting this kind of instruction or of programs. And the thing is that this is done in the compilation process. So these rules are enforced at compilation time, and we don't pay an extra cost at runtime. So it's another characteristic of this speed in Rust. Okay. So as I said, the compiler will be enforcing these rules, and we should follow these rules in our software, in our programs. Okay, we will dive a little bit in the idea of this theory. How these bugs arise. The problem in these memory bugs comes from two operations with memory. The first one is the aliasing. The aliasing is having an alias for a memory. That's two ways or more than one way to refer the same memory. Yeah, more than one path to reach the same memory. And the other action is the mutation. It's changing memory, shared memory. So if we do one of these actions, there is no problem. But if we want to do both of them at the same time, we can arrive to these kind of problems of memory bugs. For example, use after release, accessing a memory that was previously released. So the solution is to use one or the other, but not both of these actions at the same time. This was inspired in a design pattern using C++, which is called RAII, which means resource acquisition is initialization. And these rules are formalized in the type system, Rust type system. This Rust has a linear substructural type system. I don't want to enter in the theory of this type system. I just want to give you the rules of the ownership. But there's a big theory of type systems, and this is a type system that Rust adopts. Okay? This is the same pattern. Says that a resource, the memory, is initialized when it's allocated. Initialization is done in class constructors. The cleanup is done in the release is done in the destructors. And the destructors are invoked automatically when the variable goes out of the scope. Yeah, this is done automatically by the compiler. Okay. In C or in C++, an instance of a class, an object, owns another object that's pointed by that one. That means that this object, the owner, can decide when to release the object, the possessive object. Because the owner can decide when to release the possessive object. So when the owner is destroyed, all the possessions are destroyed as well. So with this inspiration, there are the rules of ownership in Rust. There are 3 rules just 3 rules of ownership. The first rule is that each value in Rust has a variable that is its owner. Okay, we have a portion in memory containing a string. I have a variable that is the owner of this value, of this string. The second rule is that there can be only one owner at a time. And the third rule is that when the owner goes out of the scope, the value will be released. The value owned will be released. These are the 3 rules of ownership of Rust. So it implies that each value has a unique owner determining its lifetime. What's the lifetime? The lifetime is a portion in our code where the value lives. We will talk about lifetime in some minutes. So when the owner of the value is dropped, that owned value is also dropped.
Pablo, I have a question there. Imagine that you want to return a string or some dynamic data structure, right, like that.
Yeah.
And I guess that because it's dynamic, the data goes into the heap, but the pointer is in the stack.
Yeah.
Right? So if I create that dynamic data type inside a function and I want to return its value, what it gets destroyed is the pointer in the heap, but not the value in the, sorry, no, it's the pointer in the stack, not the value in the heap, right? Is it like that?
Yeah.
Is that correct?
Yeah. You can transfer the ownership of the value.
So what about if I return a slice? Is that possible?
You can return a slice. Yes, you can return a slice. That's a value in the stack, a fixed value, for example, an array. And you can also return a reference, as we will see in some minutes. Let me show you some examples of functions and return values. The idea is that the owner owns its value. And this owner is a variable. And when this variable its control block leaves the scope, the variable is destroyed. So the value in the heap, for example, as you said, will be destroyed. These are the rules of ownership in Rust. We will see all the implicances of these rules and the problems for us being developers. Look at this. This is a taxonomy of the ownership, showing us that the symbol T represents any data type. When we put T, we mean that we are talking about the owner of the value. So if we are the owner of a value, this is mutable. We can get a reference for t, which is ampersand t, and this is called a shared reference. So this is an alias. We cannot mutate the content of the value. And we can have a mutable reference, and we write this as ampersand mut t, and we can mutate the content of the value. So we can have the value mutable or shared, but not both at the same time. That's the key of ownership in Rust. Example. We have this function print Padawan. Padawan is like a Fibonacci series, but a bit different. Defined like this. The next value in Padawan is the element 3 positions before plus the element 2 positions before my index. Yeah, similar to Fibonacci. So look at this. I create a vector. I initialize it with 3 ones, 1, 1, 1. And then I do an iteration starting in 3 until 10, but not including 10. Because I want to have 10 elements, and the first element is 0. So I am pushing in every step the next element of the Padawan series. Okay? And then I print with this print line, I print the whole vector with the debug trait. This question mark and 2 points is the debug trait invocation. So Padawan is a vector. The content of the vector is allocated in a heap. The vector was allocated here, and the vector was released and destroyed at the end of the function. Okay, so we have the heap. The heap contains the elements of the vector. Okay? And in Rust, vectors have a capacity and a length. Length is the actual size of the vector, and capacity is the reserved space for the vector. So this is a kind of a pointer, which is called a fat pointer. It's a pointer with more information, and this pointer is in the stack and has a pointer to the beginning of the vector in the heap. This element in the stack is my variable Padawan. Okay? Are you okay? Yes? Okay. Cool. Look at this example. I have this little scope defined with these curly braces. I define my variable point. Point is a tuple like this, a tuple of 2 floats, but this tuple is inside a box. What is a box in Rust? It's a data type that allocates the content in the heap. So I am allocating the content of this tuple in the heap. So in this first line, I assign the point, this value to the point variable. In the second line, I have this variable label, and I create a string. This macro format is a macro that creates a string with the format of this format representation. It's like the string f or print f, print with format, or of C, given as a buffer. This gives a string. So it creates a string with the representation of the point in the debug manner, calling the debug tray because it has the question mark. So I can assert with assert equals that label equals this string. So this example is just to show you that at this point, at the end of the curly braces, both variables, point and label, are destroyed, are free. How does it work in the memory? I have the heap for the point. The heap contains the actual value of both floats, two values of the floats, and in the stack, I have the pointer to that memory in the heap, and that's my point variable. So the box T is a generic because the box can contain any data type. It's a pointer to a value stored in the heap. So calling box new, like in my previous slides, box new, allocates the space in the heap and moves the value v to that space in the heap and returns the pointer allocated in the stack, the pointer pointing to the heap. So the box is the owner of the space in the heap that it points to. So when the box is destroyed, that space is also free. And the same happens with the label. Label is just a string. But in this case, the string is more complicated than a simple box. And the string is a pointer in the stack. It's again a fat pointer with a length and a capacity, and it points to a region, to a memory in the heap. And in the heap, we have the succession of chars. So in this case, the label is the owner of the space in the heap. Okay. Look at this example. We have a struct, the declaration of a struct person. Person is a struct having two members, two attributes, name, which is a string, and birth, which is a integer of 32 bits. Person. So I declare a vector with this vec new. This vec new is constructing a vector, an empty vector, and I call this variable composers. And I declare this variable mutable with this modifier mute, and then I push elements to this vector. I push the first person, creating this person in line. The struct person, I give this a name, string, and a birth, the year of birth. Why not use iter for loop?
I mean the ampersand inside in the front of composers, right? Or is it the same? Just the same?
I think it's the same. Yeah. I should have used .iter to be more clear. Yeah. Composers.iter is valid? Yes, of course, it's valid.
Yeah, I think if you run Clippy there, you should use .iter.
Yes.
Probably, right?
Yes. I should have used .iter in this case. Yes, of course. Thank you. Iter gives me a reference to the element on each iteration of the for loop. Okay. So I create a vector, I push the persons, each person has a name, which is a string, and then I do this iteration and I print the name and the birth. So look at the memory. The memory of this program will be like this. I have the heap, I have the stack. In the stack, I have the vector called composers. This vector has the vector called buffer pointing to the heap, the capacity, and the length. The capacity is usually greater than the length or the same size as the length of the vector. The length is the actual length of the vector. So in the heap, we have every person, one, and then the other, and then the other, all together. And the person is a grouping of name and the birth. Name is in turn a string. A string is another fat pointer with buffer, capacity, and length. So each name has a pointer to another space in the heap, pointing to the actual string containing the name. But the capacity and the line are in this part of the fat pointer. So the birth is next to the name, to the fat pointer of the name. So that is the map of the memory when we run this program. When we use into iter and iter mut. Okay. Okay. Let's go back. If in this example I use .iter, just .iter, I am iterating over references to each element. So I am pointing, having pointers to each element in each iteration of the loop, of the for loop. If I use into iter, I am getting in each iteration of the for loop, I will get an own element of the vector, not just a reference of the vector. So with into iter, I am kind of visiting the vector and getting every element out of the vector. I am consuming every element of the vector. So the vector won't be accessible after that iteration, after that for loop. I am transferring the ownership, as we will see in some minutes, with into iter. And I will get the ownership of every element in each iteration of the loop. And with iter_mut, I am getting a mutable reference, like in the case of iter, of just iter, but with iter_mut, I get a mutable reference to the element. That's the difference between these operators with iterators.
But what happens if you then use into iter? You transfer the ownership, and then the for loop ends, and then that means that it will the memory will be released, right?
Let me write to owner transfer
Okay.
in some minutes.
Yeah.
Okay. Let's continue with this. So, to recapitulate, we have the rules of ownership. So each value has a single owner. So with this rule, it's easy to decide when to destroy the owned value, because we have just only one owner. But an owner, a value owner, can be owner of other values, as we saw in the previous slide. We have a kind of tree. If we go back, this is kind of tree. We have the vector owning this memory, and this memory is owner of this, or the person is owning other portions of the memory. Okay, so we can have trees of regions of memory, of values, better said. In Rust, we typically don't destroy values explicitly. It's not common to explicitly destroy the values. We can do that, we have methods for that, but it's not common to do that, because we let the compiler to do that when the value goes up from scope. And destroying a value means that we have to remove that value from that membership tree in some way. That's destroying a value. So we can see that in this way, Rust is less powerful than other languages like C, because we are restricted in this by these rules to manage the memory. Okay. So Rust is less powerful, but it's like Rust is protecting us from making errors. We will talk about movements. In Rust, like in C++, values can be moved from one owner to another owner. So doing this, we can build, we can rearrange, or we can tear down the tree we have. Okay. In the standard library, we have methods and tools providing us reference counting pointer types. They are the RC and the ARC. These tools, these structs, make us or give us the possibility to have multiple owners, but under certain conditions and restrictions. Okay, so in general terms, we have only one owner, and we can transfer the ownership of a value from one owner to another. But we can borrow a reference to a value. So references in Rust are pointers that are not the owners of the value, but point to them and have limited lifetime. So the lifetime of the references are smaller than the lifetime of the owner, or must be smaller than the lifetime of the owner. Okay? So in Rust, there are many operations that moves values. For example, assigning a value to a variable produces a movement. Passing a value to a function produces a movement. And returning a value from a function, a value not implementing the copy trait, produces a movement as well. So, Marcos, if you return a string from a function, you are producing a movement of the string from the function, inside of the function, to the caller of the function.
What is then the best way to return a string or a dynamic data type? Like you use clone or just
No. You need to return a string. You don't clone. Okay. So when we move the value from one owner to another, for example, I have a vector and let me look at this. I have this example. I have the variable a. A is a mutable variable. So I assign this person to the variable. And then I assign another person, a different person, to the same variable. Doing this assignment, Rust is destroying the area, destroying the value that was previously assigned. It's destroying the first person. For example, no. Shadowing is when I use the same name for a new variable, but not when I change the content of the variable. Shadowing is when I use let again to reuse the same name for another thing. But in this case, I don't have let again. When I have let for the same name, it's shadowing. This is not shadowing. Okay, cool. Other examples for movements. When I return a value from the function, the value is moved from the function to the variable in the caller of the function. Okay. When I construct new values, the values are moved to the structs and then to the caller of the function. Okay. When I construct new values, the values are moved to the structs and then to the caller of the function. Okay. When I construct new values, the values are moved to the structs and then to the caller of the function. Okay. When I construct new values, the values are moved to the structs and then to the extra variable. Look at this. When I pass the value to a function as an argument of the function, for example, this f and the argument x. I have a person, this person, this is a little tree, as we saw before, and I am passing this argument to the function f with argument x. And what if I use x after calling the function? I will get an error, because doing this, if this function receives a person, I am transferring a movement, the ownership, from this value to the function. So if I try to access x after calling the function, I will get an error, a compilation error, because I lost the ownership of the value in this case, because the function receives this function f, this particular function f, received the ownership of the value.
Pablo, then after using f, the variable x has to be free, right? The memory, all the memory is free.
The value of x was moved inside f, and the variable x was marked as invalid. So
yeah,
I cannot.
My point that all the memory that was being used by x just is freed, right?
Yes.
Because the owner is inside f, so the owner
is inside f, and then the rules of ownership counts for f right now. So if f finished, f must destroy the value, the content. But in turn, f can return the ownership again to another caller. So the value won't be free on that case.
Yeah, perfect.
Okay. So in this case, calling a function that receives the value produces a movement. I'm moving the ownership, moving the value to the function. An example of a movement with an assignment. I have this vector. This is a vector of strings, a vector s, and then I assign s to t. And then I assign s to u. So it's clear that I'm not able to do that. I will receive a nice error telling me that. And the error says, use of moved value s. I give the line where I'm doing this, line 9 is the source of the error when I try to assign s to u. And the reason of the error is s. Move occurs because s has type vec of a strings, and this data type does not implement the copy trait. And then the value was moved here when I assigned s to t, and the value was used after move. Okay, that's a very common error we can get in Rust, trying to compile a Rust code. Do you see this? Any questions? Apart from Marcos, who is the only one having the camera on.
Yeah, also to make it a little more dynamic, right? Yeah, right. Going to the example of the X variable that you pass to F, right? I think that the best, if you have a dynamic data type there like a vector, you can just borrow the value there, right? You pass a reference, like
yes.
Then you can change it inside F, and you don't return anything, but the changes occur in the X.
Of course, of course. That depends on the signature of the function. But if the function receives all the ownership of the variable, you're producing a movement. Perfect. Okay, so what does this mean? S does not implement the copy trait. Who wants to answer this? Somebody? No? What does it mean that a variable implements the copy trait? What do you think from this error?
Oh, maybe it means that it can be cloned.
Okay. Data type implements the copy trait when it's cheap to copy the, in general terms, when it's cheap to copy the content from the source to the destination. So the primitive types, if we can say that word primitive, like the integers or floats or booleans, implement copy trait. Because it's cheap to copy an integer, 32 bits integer from one side to another side. In fact, it's cheaper than copying the fat pointer of a vector. Okay, but copying or cloning, allocating space for new memory, duplicating the memory for a whole vector is not cheap. So vectors don't implement copy trait. You cannot copy a vector. You can clone a vector. You clone a vector when you create a new vector, allocate in a heap, and you duplicate this memory in the heap. So types that are allocated in the stack implement copy traits. Okay.
Pablo, it happened to me before also that I made a struct, right? And one of the fields was a vector, right?
Yeah.
And I tried to derive the copy trait, but it didn't work, right? Because I think I read somewhere in the internet that it's not good to implement the copy trait. Is that correct or not?
Yes, it's not good to implement the copy trait. Yes, it's not, in general, it's not a good idea to implement the copy trait in your own data type.
Why is that?
Because when you implement the copy trait, you are doing this operation. You are doing a duplication of memory transparent in a way that is transparent for the user of your data type, but is doing a hard computation or a computation that is expensive. Or you're allocating more memory than necessary. Imagine that I implement the copy trait for the person, and I do this that I was doing before. This. I am creating new memory every time I do this without realizing that I'm creating memory. Okay.
Yeah, perfect.
Did I convince you?
Yeah, definitely. Yeah.
Okay. So let's move on. More about movements. Yes. Proto.
Yeah.
Is
Well,
it okay to say proto?
No, it's me, alias. My name is
Okay.
Chris. Yeah.
Okay.
What about using the clone method? It is awful to use it because they always say that you don't like. I don't need to use it because it will have an impact in performance. So instead of that, I need to use like a multiple reference. Is that correct or not?
Okay. It's not that it's wrong. It has an impact in performance and in the usage of memory, but in some cases you cannot avoid using clone. But the thing is that when you use clone, you are being explicit. You are putting a method clone in your code. Instead, when you use copy, you are not putting copy in your code. So you should avoid using clone to avoid paying that cost of more memory usage, more computation. But in some cases, I think that it's easy to use clone that no using it. When we are doing a performance analysis or we want to write a performance library, we should avoid clone every time we can. We should be we should use more references every time we can and avoid using clone. Okay, so when a value move and we don't assign a new value to that variable, for Rust, for a compiler, this variable is considered uninitialized or uninitialized. In the previous example, when I move S to T, S is considered uninitialized from this point. So I cannot use S anymore. So look at this example. I have a vector X and if I pass this vector X to a function, I am doing a movement of X to the function, for example, the function F. Look at this case with the if. I have an if, checking for a condition C. If the condition is true, I am executing F with the argument X. If the condition is false, I am executing G with the argument with the same X. Both of them produces the movement, but the compiler allows me to do that because only one branch is executed because there is an if. So there is a movement in both of the branch, but in this case, it's okay to do that. But I cannot do another movement or another usage of X after the if, because X was used even on F or on G. So I will get the error when I try to use X in the H invocation. Can you see this? Yeah? Okay, I assume yes. So in the general case, moving a variable in a loop is forbidden. Look at this example. If I have a while, I cannot move the same variable inside the loop because the variable was moved on the first iteration of the loop. So I'm not x is uninitialized for the second iteration of the loop. Marco says you can borrow there. Yes, I can borrow the value, but I cannot. I am not the owner anymore if I do this. Yeah. Other operations that move. So suppose that I have a vector of strings like this. For a vector, and I do a for loop and push elements inside the vector. And then if I do random access to the vector, I am moving the element out of the vector. So that's impossible, or that's not allowed. Because I cannot move a part of the vector out of the vector. And I get this error, and this error is telling me that this is a vector of a string. A string does not implement the copy trait, so I am moving it. So the hint of the compiler is use a reference or get a reference to that element of the vector with the ampersand. Okay, in that case, I'm not moving, I am just getting a borrow of the element, a reference. Yes.
Sure. Let me know if I'm getting this straight. If I do a reference, right, it's like some kind I have permission to read. And if I do a reference with mutable, it's like I have a permission to write it. Like it will change it. Is that true?
Is that true? Yes.
Okay. Okay, got it.
This is true. You have the permission to access to it.
Okay, thanks.
It's like you have the borrow, you have the permission, but you cannot control the lifetime of that content. You cannot destroy the content. Okay, so we saw that there are many operations producing movements. So we should take care of it. We will, if we get these errors, these kind of errors, when trying to compile the code, like the ones I showed in the previous slide, maybe we could start fighting the compiler. That could be a big fight. The compiler doesn't like to lose the battles, so instead of fighting against the compiler, sometimes we should stop and think if our algorithm, our code is okay, or we have to change our algorithm, our pattern, our design of the algorithm, and not try to push the compiler to accept our code. Okay. For example, suppose the previous example, I try to take the ownership of these two elements. Okay, I cannot do that, but in the standard library, or doing an iteration, I can iterate the loop having the ownership of each element in each iteration of the loop, I'm assuming all the vector, the whole vector. So the vector will remain on an initialized state after that for loop. So that's a different design pattern for my algorithm. It's different from assessing in the random way. Okay, and that's similar for other collections that we have in the standard library. For example, we can use these methods like pop, for example. Pop removes a value or the value from the end of the vector and gives us the value or the ownership of the value. Produces the movement of that value to our new variable with pop. Pop also returns a result, but that's not important here. So with pop, we are not doing a random access to the vector. We are just getting the ownership of the last element of the vector and removing it from the vector. We also have, if we don't use the unwrap, the type will be result specialized in a string, because it is a vector of strings. So we should use, in this case, instead of using unwrap, you don't use unwrap in here, you shouldn't use unwrap in this case. You should use, for example, the mark, and if we get an error, we should return from the function, for example. Sorry, I was wrong. The type here is not the result, it's the option. Sorry. The option of a string. So if the vector is empty, we get the known variant of the option. And if there is an element, we get the sum element with the ownership. Sorry. And the question mark is the same. Question mark for only the success value. I don't understand the question.
Yeah, sure. I don't talk that much because there is some construction going on here. I use the that operator, but only I will handle if I have a string, right? Like if I do not have the string, it will not have any value, or not.
If you don't have the string, the question mark will return from the function where
The
that
error.
is called. Yes, returning the known in this case.
Okay.
Aniket says, if I use a wrapper 100, if there is no element left, will result in 100? Yes, it will construct a new string 100. Yes. Okay, so you have pop, for example, to avoid this random access. You also have, for example, swap remove. Swap remove is give me your value and I give you this value. So it transfers the ownership of the value. And it replace the value I am pointing with the last one. And for example,
what if I sorry?
no, Marcos.
So what if I want to copy an element from the vector without removing it from the vector? So is there a copy method or something?
Yes, you can do that. You can get the reference, like in the previous slide. Yeah, like this, ampersand v2, for example, and then you can clone that element, for example. With a reference, you can build a new element from a reference, copying the content of the reference.
Okay.
And then you have this replace method of the mem module of the standard library that substitutes the content of the vector with the other content we are giving to the function. So we get the ownership of this value that was previously in the vector, but on that place we are putting a new value. It's like we are fixing a hole with a new value. We cannot get holes in a vector. So in that place, in that hole, we are putting this substitute string. And we get the value that was previously there. Okay, that's all of these are just ideas for you to avoid fighting the compiler. Okay, so as we previously said, we can iterate a vector consuming the whole vector. Like in this example, we can get mutual references for every element of the vector. So in each iteration of the for, we have a new mutable reference to the elements of the vector. So if we pass the type t, if we pass the vector to a for iteration, a for loop, we are moving the vector to the loop. So after the for loop finish, this variable b remains uninitialized. Okay. Is it clear? Okay.
Yes.
Okay. Okay. So there are types that are copied instead of moved. For example, we talk about types that are primitive types. Yes, types that are byte to byte copied. So when we do an assignment, the source remains the same, and we get a copy of the element. When we call a function with a type implementing copy, it's the same. The source value remains intact. In general, when it's just copying byte by byte the content of the value, this type implements copy, integers, floating points, char, bool, etc. If we have a tuple and all the elements of the or components of the tuple implements copy, the tuple automatically implements copy. And if we have values that have something else, something more than just the content, like the integer, in general, that value cannot be copied. Or if we need to do something more when the value is destroyed, that element does not implement copy and shouldn't implement copy. Okay, so in the case of the vector, for example, when we destroy the vector, we need to do more things than just destroying the pointer. Remember the tree we had before, we should destroy the whole tree. So that's the thing with copy. For example, I said that tuples automatically implement copy, but structs and enums don't implement copy automatically. But if all the fields, all the components of a struct implement copy, we can make the struct implementing copy. We just add this derive copy and clone on the definition to the definition of the struct before the definition of the struct. So in the case we have a struct having just only one field, it could be a good idea in this case having copy trait implemented for this struct. So I can do this adding this derive because the struct is just a number. Okay. But in the example I said before, when Marcos asked, it's not a good idea to copy automatically a vector of composers. Is it okay? Yeah. Okay. Okay. Let's move to references. We have a string. I call this S1. I construct a string with this method. This is like the new. This allocate the space in the heap and put this content in a heap. And then I have this function calculate length. Calculate length receive the whole string. Look at this. It receives the own string and returns the integer, the usize, telling the size of the string. Okay, so the body of this function is trivial. So when I call the function with S1, I am transferring the ownership of the string to the function. So in this example, if I am distracted and I use S1 after calling the function, the call will give an error. Look at the error. It says that the value of S1 was moved in the, it says was moved here, calculate length was moved here, and it says that I am trying to use it in the print, and I am borrowing the value after a move. Yes, I go back to the previous slide. Yes. So this function is getting the ownership. The string is being moved to the function in this case. So the error is that I cannot borrow this print line macro is borrowing S1. I cannot get a borrow after a variable was moved. Okay? This is the error explaining that. So we can do the first attempt could be this one. I can move the string out of the function again. I can return the string again. So I can have calculate length, receiving the whole string, and returning a new string and the size I wanted to return. So I can return a tuple with the string and the length. So in this case, I will call the function and I will give a string s2 and the length I wanted. So now, as in the previous example, in the print, s1 is invalid because it was moved, but now I have s2. So I am able to print s2, and this works. Okay? Do you agree that this works? Yeah. Okay.
Pablo, can you make S1 equals to calculate length?
Yes. I am it's just reusing the same name. Have the same effect. But what's the problem with this code? You want to try an answer?
Is there a problem? I don't see a problem.
Somebody else? Do you like this code? This example?
Should I have a reference to length?
Someone says it's not efficient. I shouldn't say it's not efficient. Yeah, it's not efficient, but the main problem is not that one. The problem is that I have to add an extra variable each time I call a function. So I am giving you a parameter, an argument for a function, and you should give me the argument again back. It's awful.
But
It's ugly.
then I imagine that when you return S in calculate length, well,
Yeah.
you're just moving the value, right? So in the stack there, I mean, I think the stack, in the stack you only change the reference, right?
The heap remains intact.
Yeah.
But in the stack, the pointers are created again.
Yeah, there's an S2 in the stack that points to the heap, to the same.
Yes, and the heap is the same.
Yeah.
I have a new variable S2 in the stack pointing to the same heap.
Well, it's not like it's not efficient. There's just a new name, right?
Yes, it's ugly. It's not comfortable for the developer to catch the value again. Okay. So the solution could be this: to have the function receiving a reference to a string and returning the size. So now the function is receiving a borrow to the string. So after calling the function, S1 remains valid. And I can use S1 as before, because in the print line, S1 is still the owner of the value. So the print line takes another borrow of the value. So that's why reference exists. Most of the types of pointers are the owners of the data in the heap, right? So references are a new type of pointer, but not taking the ownership of the value, but borrowing that content. So references don't affect the lifetime of the reference. And of course, the references should not survive the reference. I mean, references should not survive the owner of the element. So when I do a borrow, this process of borrowing is set to create a reference to the value. Okay. In Rust, references are always valid. If we have a reference, we are sure that this is a pointer pointing to a valid value. And in Rust, references are just memory addresses containing an address of memory. Okay. And a reference allows me to access the value, not affecting the membership, as somebody else said before. Like this, somebody said, I think that Proto said that I get the permission to read the content. Okay. So remember the table we presented before. If I have a shared reference, we have alias of that content because we can reach the content via two paths, but we cannot mutate that content from two places. We have two types of references in Rust. The first time is this type we just saw, the shared reference, that allows us to make a reference that can access the content as a reader, but not without the permission to modify it. And as such, we can have as many shared references as we want at any time. All of them having the permission to read the content. And we have the mutable references to values. And with that reference, we can read and modify the value, but we cannot have any other active reference of any type, not shared and not mutable, at the same time. Okay? That's the consequence of the rules of ownership in Rust. Okay, so in Rust, references has no initial value. There are no default value for references. There are no null pointer value, no things like that. And in Rust, we cannot do arithmetic with references. We cannot add an integer to have a new memory address like we can do in C language. So references are always valid, and if we want to indicate that we have the absence of a value, we use the option that we talked before, the option, and we have the non-variant of the option to indicate that. But we don't use memory addresses to indicate that there is no value on a variable. So look at this example. We have a hash map. Yeah, hash map with where key are strings and the values are vectors of strings. And I create a table. This keyword type in Rust is just an alias. It's a new alias. I define a data type. I put a name to a data type. It's just an alias, not more than that. I create a variable called table, which is a hash map, and then insert some content to that hash map. Yes, Gesualdo and musicians and content. Yes, type is just the type def. Yes, no more than that, just an alias for the type. And I insert some elements to the hash map, okay? And then I call show. So show receives the table. Look at this. Show receives the ownership of the element. So inside the function, I can do whatever I want because this function is now the owner of the content. So I can iterate and I can print the content of the hash map in this way. And what's the problem? That in the main, I wanted to, again, to use, I put show table and then I have an assert table and I am accessing an element of the table. And of course, I cannot do that because I get the errors telling me that I move the variable table calling the function show. Okay, that's similar than the case we presented before. And the hash map, of course, does not implement the copy trace. Okay? So, to correct that, I can receive a reference to the table in the function. So I have a reference that gives me the permission to read the table in the show function. So then on my main function, I can call show giving it a reference to the variable, not the variable itself. So that's work. Questions so far? Somebody wants to say something? No?
Hey Pablo, before we continue, I wanted to ask about the unwrap and unwrap OR. Can I ask about that at this time?
Yeah.
Yeah. So The other useful operations was is some, is none, is okay, is error. All of these are Boolean type, right?
Is some, is none, is okay. Yes, all of
Yes.
them
Okay.
are Boolean.
And
They
to
return a Boolean. Yeah.
okay, yes. And in unwrap and unwrap or, uh, I was unable to uh, categorize is at as a another operation because it it is doing the same implementation as match. Is it right, or I'm unable to differentiate between unwrap and match? Uh,
Okay. No, they are different.
yes.
When okay, when you use unwrap, the return type of the unwrap is the type of your generic type option or your result, the type T. The unwrap is, if you want to use a match, you have the sum branch and you do something, and then you have none branch. If you put a panic, an explicit panic to abort your program in the none branch, you are doing more or less what unwrap does.
So like we can do the same thing with match what wrap does, but not the same thing with unwrap that match does, something like this.
With unwrap or you mean you
Yeah,
can
like
put
yeah, we can do the same thing with match uh, does that unwrap does, but we cannot do the like opposite. Uh, Whatever unwrap can do, match is not suitable for that. Or I'm confused because in both cases we have none and some. So maybe I will get a hold. I'm just confused at the
okay,
moment. Like,
we're going to see some examples later.
okay, that's
Running code if you want.
that's good. Thank you. Thank you.
Okay, let's continue with references, and we're close to the end. No, we have no much more than this. So to recap, each reference has its own lifetime. The lifetime is a piece of code. It's an area on your code where the reference is valid or is used. So the lifetime of a variable, in particular of a reference, is automatically derived from the way you use the reference. Okay, this lifetime could be an entire function or a block or just one line, 2 lines, and a scope, or the scope of a variable. And the lifetime of the variable, of the original variable, must contain the lifetime of the reference that borrows that value. Yes, somebody wants to keep? Proto.
Sorry, I wasn't talking.
Okay, you were mute. Okay, so when you have so the original value, the owner of the value have a lifetime of the whole value, okay, containing the lifetime of the reference. So when the value is freed or is destroyed, or the value goes out of scope, the references will be invalid. And that's what we call a dangling pointer or a dangling reference. So the compiler checks for that, and the compiler doesn't allow us to use a reference beyond the lifetime of the owner of the variable. We will see that in a minute in an example. Look at this. Look at this simple example. We have a definition of a variable R, and then we have an inner scope, and then we assign 1 to the variable X, and then we create a reference of X and assign it to a variable R. And then in the outer scope, we assert the destination of the reference with 1. Okay. And what's the problem with this code?
I think it's supposed to be immutable because R first is not mutable. So we are changing the value of R from default to the reference of
That's
R.
not the problem, because R is not mutable because I'm using just let, but since I'm not assigning an initial value here with let, I can assign a value later on. Okay,
Oh,
Musa?
okay. Yeah, I get it now.
Okay. Yagna says it's not in the scope.
Yeah, what's wrong is X, the lifetime of X is already over because X has gone out of scope by the time you are
Exactly.
set R.
Exactly. The owner of the value gets out of the scope, so the value contained in X is destroyed, and we want to hold a reference after that point. So that's invalid. That's not possible. If we try to compile this, we'll get this error. Borrowed value does not live long enough. And the compiler says that the value is dropped in this curly brace, where the scope finishes. Okay? Do you agree?
Yes.
Yes, perfect. So here, if we drop the lifetime of the variables, we have at first, if the lifetime of the if the assert is inside the curly braces, it will show an error. Yes, of course. Exactly. Here we have the lifetime of the reference of X in this diagram. Okay, and the lifetime of this reference finish at the end of the scope. That's the first lifetime. Then we have the lifetime of the value stored in R. It starts when the value is assigned to R, and it finishes the last time we use it in the assert. So since we store a reference in R, we need the lifetime of the reference stored in R to be valid for the entire lifetime of the variable R. And we have this. we have that the lifetime of the element stored in R is this first rectangle, and we have that the lifetime of R is the other rectangle, the second one. And we need the reference to be inside the first rectangle to be inside the second one, okay? So that's the notion of lifetimes, the portion of code where this value is valid. And that's the reason that the compiler is giving us the error. Okay. So both variables are controlling the lifetime of the reference. With one, we are controlling where it starts, and with the other one, where the lifetime finish. If we put the assert inside the block, as one of you said, everything is okay, because one rectangle fits inside the other one. The lifetime of the reference of ampersand x is inside the lifetime of R. Okay? Questions so far? Cool. One more thing about the references, how to work with references as parameters of functions and references inside structs. Look at this code. This code, we will show you first an ugly code to understand the problem of this, and then we will see more concrete examples. This code, this function, f receives a reference to an I32 in the variable p and stores this reference on a global variable. This is horrible. Using global variables is horrible. Don't use global variables. This is just an academic example to show references and lifetimes. Okay. How do we know this is a global variable? Because we defined this with static at the beginning of our program. Okay, just for the example. So the static modifier or keyword tell us that the value of this variable should be valid since the program starts and until the program ends. So static variables in Rust follow these rules. The first rule is that every static variable must be initialized. So this is an error. In this code, I'm not initializing the value. Other rule is that mutable static variables are thread unsafe. I cannot share this kind of variables between threads. And even more, in a single thread program, I cannot access this global variable without using unsafe. Okay. Okay. But with all of that, I want to use this to show you the logic of references in this example. So, okay, I can follow the rules or try to follow the rules and correct this example. So they tell me, okay, I have to initialize the value. Okay, I initialize the stash variable. with a dummy value like this, ampersand 128. And then I have the function, and they said, okay, you have to use unsafe. Okay, I put this block inside unsafe. Okay, and what's the problem with this? The problem is that the lifetime I am using a function, I'm declaring a function, receiving a reference, and I need to make the lifetime of this reference explicit in the declaration of the function. Okay, so every time you receive references in functions, we need to express that lifetime, the lifetime needed. There are some cases, or many cases, where the compiler can guess that lifetime, but in other cases, like this one, the compiler cannot guess that, or the compiler wants us to make it explicit. So the compiler is telling me to add this modifier. This is the lifetime, an explicit lifetime, the tick static. Ampersand tick static is the name of the lifetime. I am just putting a name. It's not a modifier of the name. It's just putting a name to that rectangle. But I cannot change the shape of the rectangle or the size of the rectangle I showed before. So why tick static? Because static is a special lifetime that must be valid across all the program. And the compiler guesses that because I visit the variable p in this way, assigning it to the stash global variable. Okay, so I can name a lifetime. If I name a lifetime, I can use any name. Static is the only reserved word name for lifetimes, but you can name lifetimes with the name you want. At the beginning in Rust, it was common to use single letters to name lifetimes. Nowadays, it's better to use more words than single letters. Okay, but I can use tick A in the parameter of the function, and as in the case of generics, I have to put this here inside the angle brackets. Yeah. So I'm naming the lifetime of the reference of the variable received by the function. So here I corrected a little bit the code, but it's still insufficient because I am using this variable to assign the value, the reference, to the static variable. So tick A is not tick static. It's not assured that tick A will be as long as tick static. Okay. So the only way to have this working is to use the static lifetime for this. Okay. This is a completely extreme example I wanted to show you to understand the relationship between the rectangles of lifetimes of references in Rust. So why does the compiler need this? Because the compiler uses the declaration of the function to check that the relation, to check and to evaluate and the relation between the parameters and the return type is being doing correctly. So that's the reason I have to, if I receive a reference, I have to make this explicit, except in cases the compiler can infer it, and that's called lifetime elision. Okay, so we also can have structs containing references, not only own types, as we saw before. We can have references in the fields of an struct. Like this example, I have the struct S, and I have a field called R containing a reference to an integer 32 bits. What's the problem with this? The problem is that if we have a type containing a reference inside, we have to make the lifetime explicit. So if we try to compile this little example, we will get this error. Missing lifetime specifier, expect lifetime parameter. So to correct this, we should specify the name of the lifetime of every field containing a reference in my struct. In this case, I can put a name or a descriptive name. I just put A, and I must put these lifetimes inside the Engr brackets. So the compiler knows that every time I create a new value of this type S, this type gets a new lifetime tick A. This tick A is restricted depending the use I give to the value. Okay? Is it clear? So, like in the previous example, I can do the same for my struct. The previous example I have with the air and the X, I can do the same with the whole struct. I have my let S, and inside the inner scope, I have a new variable X with value 10, and then I create S being the struct, and I assign to the field R, which is the only field of the struct, a reference to X. So that's the reason I can avoid writing the type here. Let S, I should have put the type in this let declaration, the first line, but the compiler can infer from the use in this assignment. So again, if I do this assert the queue, and I use the content of the struct, I have the same error or a similar error, because as we saw, we have the same problem as before with the two rectangles. I am having a reference, and the owned value is dropped before I use the reference to that owned value. Okay. So the reference to an owned value must be inside the lifetime of that owned value. Okay. Any questions about that? Okay. I think these are the hardest points of Rust. Suppose I have a struct with two fields. I call this struct extrema. I want to model the beginning and the end of a range, for example, or the greater and the lowest number, for example. So if I don't want to copy the values, I can use this struct to store just reference to that values and not the whole value. In the case of I32, it's not efficient, it's not an advantage to do this way, but this data type could be a more complex data type, like a big tree, for example, or a hash map. So since I am storing references to values, I should name the lifetime for these references. I must name the lifetime for the references, and I must declare this name at the beginning of the struct inside these angle brackets. Okay, so I put this name, ELT. In this case, I am saying that both fields have references and they will have the same lifetime. That's the reason I put the same name to both lifetimes. If I need to model something with different lifetimes for each field, I should use two different names. But this is not necessary in this example. So how do we use this? I have a function, find extrema. This function receives a slice, which is a reference to an array of I32. And returns a new element, a new struct of this type, extrema, that contains the references. So with this first line, the declaration of the function, I am telling that the lifetime of the object I am returning in this function, which is extrema, has the same lifetime of the parameter given to the function. I am telling the relationship of the references, the input reference and the output reference I am given as a result. That's showing this, the relationship between the lifetime of the references. So as always, if I have references and lifetimes in functions or in parameters, I have to declare this in these angle brackets. And then inside the body of the function, I can use the references following these rules. If I am creating a new object, a new struct, I can be sure that the lifetime is okay because I am returning something with the same lifetime as the input. So I am doing an algorithm that copies references. At the beginning, they are both the first element, references to the first element, and then in a for loop, I am checking the condition that telling if the element is lower than the one I had or greater. And then I have a new reference to the new element. And at the end, I construct a struct with the references. So here, I'm not copying the content of the numbers. I'm just copying the references to that numbers, to that specific elements of this array of elements. Okay. Is it example clear? Yeah? No? Okay. Thank you for the reactions. Okay. So how do we use this? As usual, I have my vector or my array, and I call the function find extrema, and I pass a reference to the array, and then I will get the return, which is an extrema struct. And then I access the destination of the reference using the asterisk or the star symbol. Okay, so when I invoke the function, I'm not making the lifetime explicit. I just create a reference and use it as always. Okay, and the last subject I wanted to present to you is a little bit more about generics. Okay, we already talked something about generics when we talk about options and results. We said that they are generics because we can have concrete types depending on the type of T. We are using a little bit more here. So what's the goal of generics? The goal is to avoid duplicating code for the same task, duplicating behavior and abstracting concepts in our program. It's a tool that allows us to do some kind of polymorphism. We already seen that we can do polymorphism with traits. You remember that we had some functions receiving a type that receiving an argument that we didn't know what was the concrete data type, but we asked this argument to implement a trait. Okay, the other way is to use generics. Okay, we can. Yes, Marcos.
What about the number of parameters? Can you make a function with the same name but different number of parameters?
No, not in Rust. No, that's in C++. In Rust, functions a unique name. And if you want to do that or receive a variable number of parameters, you should use a macro, as we saw before. For example, the macro vec to create a new vector and assign values in the initialization. Vec receives a variable number of parameters, but it's a macro, not a normal function. And macros are much more complicated to be defined. Okay. Do you know something about object-oriented programming or polymorphism in objects in languages like C++ or like in Java, for example, where we can have inheritance? Yeah, Musa.
Yeah, polymorphism, right?
Yeah.
Yeah, it's like where an object, like we can define something to behave differently based on the form that it is. So we can have a function that maybe based on if the type is uint is going to behave in a way. If the type is bool, so the same function is going to behave in another way. Is that?
Yeah. You can have a basic type, for example, a class figure, and then you have the squares, and then you have rectangles, and both of them inherits from figure, like for example in Java language. Okay, so if you have a method called draw, the program in runtime at the time of the execution will check which is a concrete type of our object, our variable, and we'll choose with which method execute or which method call based on that inheritance. Okay, that's in C++ or in Java. In Rust, if you use traits, with traits we are doing some kind of genericity, we abstract behavior. Does not include a cost in runtime because this is solved at compilation time. The compiler will create the code for this concrete type at the moment of the compilation, and it will add the call to that concrete function at that compilation time. So that adheres to the slogan of zero code abstractions with no penalty at runtime. Okay, that is in Java. It's called and in C++ it's called virtual methods. In Rust we don't have virtual methods. We have concrete methods, and the compiler knows which method to call at compilation. Okay. With generics, we can do a kind of a kind of polymorphism because we can have the same behavior, the same function with code for a type T, but at compilation, the compiler will create the code for the specific type that we are using. For example, if we have an option of a string, the compiler will create on our code, on our compiled code, the code for the methods for an option of strings. Okay, so that's called homomorphism. Monomorphism. Monomorphism is we create every single function for the type we are using, for every type we use. So we don't have an extra cost at runtime. Okay. As we saw before, for example, I have this trait called summary. This trait has one method. This is the declaration, the definition of the trait, with one method called summarize. Summarize receives a reference to self and returns a string. So with this declaration, the definition of the trait, we don't know what is self. When I implement this summary trait on my concrete type, for example, on my struct, my own struct, self will be the data type of my struct. And that's the concrete type used inside the method. Okay, look at this. I have my struct news article, or an article of a newspaper, for example, or a website of news. I have these fields: headline, location, author, and content. All of them are strings. I have the trait summary. So to implement the trait, I use impl summary for news article. And then I have to implement the method summarize. The same way, it should be exactly the same way as in the definition of the trait. I cannot change anything in here. Okay. Summarize receiving just ampersand, a reference to self. So inside the body of this function, of this method, I can use self, knowing that this is a reference to an instance of news article. Okay, so I can use self.headline, self.location, etc. If I implement this same trait to a different struct, I will use self for that struct. Okay, somebody asked that at the beginning of this talk in the morning, or in my morning. Okay, questions? Okay, cool.
I have a question.
Yeah.
When I import that, then if I want to get the headline and location, I will put new article that and call the function summarize, or what?
If I want to use this method, you mean?
Yep.
I can use it in different ways. If I have an instance of this new article struct, I can just call my news dot summarize, parentheses and parentheses.
Okay.
Or I can use this, I can have a function, an external function, receiving a parameter which is not a news article, but is an object implementing summary trait, as we saw before, earlier this day. You remember?
Yeah.
The V
When
and the double V.
When I have a variable that is implementing a lot of traits, all the traits that are implemented by the variable, I need to define it at the variable, or what? Like, because let's say I'm asking here for some type of variable that have the trade summary, right? But after that, I can have so many trades that I need to always put the input for that.
If you want to implement many trades, you have to do like this and implement every function, every trade.
Oh, okay.
Except for these utility trades, you can derive, for example, you can derive default in this case. If you put derive default on top of this abstract news article, the compiler will generate the default implementation automatically.
That makes sense. Thanks.
Okay, perfect. Look at this. I have another extract. The first one was news article. This news extract is a tweet. And for a tweet, I have these fields: username, content, reply. Reply now is a Boolean, and retweet, indicating if this tweet is a reply or a retweet. Okay, so now I implement the same trade summary for this new struct called tweet. So I have to implement the method summarize. This method is the same as before, receiving the reference to self. So inside I can use the fields of this struct of tweet. In this case, I just use username and content. If I go back, the previous case I was using headline, author, and location. Both of them implementing the same trait. Okay. So I can use it as usual. I can call a function. I create my struct tweet, and then if I want to call the method, I do as usual tweet dot summarize. There's a restriction. There are always restrictions in Rust of which traits we can implement for which types. Rust have this restriction that we can implement a trait. Yes, Proto.
Sorry, before you continue, I have some questions about the
yes,
the last slide.
This one or the previous one?
I have two questions actually. Why we have to use the self from chapter 10?
No, it was no. It's an error in my slide. Self is not used here.
Okay.
I was abusing of copy paste. Sorry. Okay. I can implement a trait for a type when the type is local to my crate. Crate is the project, my project, my cargo project. It's called a crate. Or when the trait is local to my crate. Or both of them. But I cannot implement a foreign trait to a foreign data type. Okay. For example, I can implement the trait display, which is in the standard library of Rust, which is a foreign trait. I can implement display for my struct tweet, because tweet is part of my own crate. It's part of my project, even if display trait is not in my crate. And I can implement the trait summary for a type of the standard library like vec, because the trait is local to my crate. Okay. Here, because one of or the trait or the struct are local to my own crate, or both of them. The idea behind this is that Rust is preventing us to create this kind of name collisions, trying to implement foreign traits to foreign types. If we have a collision in names, the compiler wouldn't know which implementation, which code to use to invoke when invoke a function or a method on a type, on our type. Okay. In Lambda works, we have some crates. You will find some crates abstracting some behavior, mathematical behavior, things like that. You will find them, and you will find the structs implementing that crates for elliptic curves or for things like that. One more thing is that if we have a function receiving if I have the previous example, when I ask the argument of the function implementing a trait, you remember the V implementing double V? If I want this argument to implement more than one trait, I use the plus sign. For example, I can have a function receiving an argument V implementing double V, where double V implements summarize plus display. Okay. You have these useful traits in the standard library. You can read about them in the documentation. From into, we just talk about them. Copy and clone, we also talk about them. Drop is invoke as a drop method invoke when the value is destroyed. The ref mut as ref mut. The ref is to define or to redefine the behavior I want to have when I ask for a reference to that element. So I don't want to deep dive more on this, but they exist. You can read them on the documentation. And to own is a trait that defines the behavior used to convert a value in an own type. So when you implement to own, you implement the logic to reserve memory, to create memory on the heap, to allocate the value provided to that method, to the to own method. So it's common to use to out method, for example, when we create a string. When we have a string, we can provide a slice, a hard-coded slice, for example. Hard-coded slice is in the code segment. I'm writing it hard-coded in my code. So I can use the method to own, invoke on this hard-coded slice, and it returns a new created string with this content copied, allocated the heap. Okay. So you remember we talk about functions. If I want to define genericity for structs, we can have abstract types as type for fields of my structs. For example, I have this struct point. I put this type T inside the angle brackets, and I have fields X of type T and Y of type T. So I am not telling which the concrete type of T in the definition of the struct. I declare this when I use the struct point. For example, if I have an integer point, I just create a point with integer values. If I want a point of floats in its fields, I create a point struct with floats in its field. Okay. So the compiler will create the code for the different types at the compilation time. It has no cost at runtime. It's efficient at runtime. Okay. Okay, you can read in the documentation about other topics of lifetimes, because lifetimes is related to other tools of the language, like interior mutability. You can mutate an interior part of the structs. This is more complex. I think we don't need to do this, but this exists. I think we don't want to use cell and ref cell inside Lambda works, but in case you are reading some third-party code, you find this exists. This is meant to to mutate inner parts of our struct. You can read about lifetimes and closures. Closures are just functions without a name. Lifetimes and iterators, lifetimes and concurrency and concurrent programming, and lifetimes with traits. Okay, that was my presentation. The slide I prepared. Bibliography for this, the official book. Official book is free, is published on the web. It's very good. I recommend this as a first point. The book from O'Reilly. Yes, I can share these slides. Yes, of course. Yes, Gabriela. Okay. The book of O'Reilly called Programming Bitcoin. No, Programming Bitcoin, no, Programming Rust. It's very good. I used the first edition for this, but there is a second edition which has some new tools of the compiler, especially in concurrent programming. And this is a very good book, Rust in Action of Tim McNamara. It's very good. It's a practical book with many examples, many pieces of code. Okay, I will share slides afterwards with you. Maybe in the group, or maybe Julieta or Diego will send the slide to you. Questions, ideas? Aguante Rust.
Okay. Firstly, thank you very much for the lecture. It's very detailed, and I must say that from some of the concepts that I've learned here, I've already like applying it already, even in using Cairo. Like this is the first time I was going to be hearing the default, so and I was able to like use it already to make a contribution. So what I'm going to ask is, if someone wants to do all these like functions that overrides like default implementations. So something like ordering of number greater than, um, multiplication, addition. So
Yes.
like if someone wants to do those things, because we are going to be applying them in maybe doing finite field and cryptography, all those stuff. So how do we work with most of those types?
Yes. Okay. Perfect. If you suppose you want to overload or to implement the addition or the addition operator, you have to implement the trait called add, which is in the standard library, and it has a method called add. But when you use okay, I will share this on my screen. Maybe like this. Okay, so this is the definition of the method. It's a method in the standard library. You can implement this method for your type. For example, like in here, for your point, you have the point with the x and the y, and then you implement add for the point. And you have to implement the add method. And then when you use this, you don't use the add method, the add invocation. You just have your first struct, your first variable, first element, and use the plus sign as usual. And add another struct of the same type. And you can do that for generics as well, with a point T, and it's okay. Okay. The only requirement is that T implements add. Does it make sense for you? Musa, no?
Yes, it does. Thank you very much.
You have here, if you see my screen, on the left, you have all the
Yes.
traits. There's a quite long list of traits you can implement in the module ops for operators inside the standard library of Rust. Add assign. Add assign is for doing this, plus an assign, bit, or all of them. Neg to negate at the beginning, okay? Subtract, subassign, etc. The reminder of the division, the modulo, like in here, which could be very useful for cryptography. I don't know if you have the sort. Yes, you can do it for polymers. Thank you, Diego. For sort, I'm not sure you can do it with a trait, but you can always implement your own sorting method if you want to do that. No. Any other questions? Diego?
Awesome, Pablo. I liked it. Yeah, there's a question.
Yeah, when you implement this for a trait, then implement for a struct, then the property of this addition for other not objects, but native types still preserved, right? For example,
Yeah.
I can still, yeah, thanks. Also,
When
there...
you implement for your struct, it's the
Yes.
it's the addition for your struct, and everything else remains intact.
Mm-hmm. Also, are there any similar things for displaying? For example, printing structs with some arbitrary manner.
Yes, you can implement the display trait for your concrete type, and you use it in printing in the format, for example. It's
Nice,
for your
thanks.
type point. Okay. I hope the things about lifetime and ownership was quite clear. Maybe with the slide you can review it. The chapter,
very good.
If you read the official book, that subject is on the chapter 4. Chapter 4 of the Rust book. This is the documentation of the library, but Rust book, Rust programming language. Yeah. Chapter 4 is ownership. Okay, I will send you some examples if you want among these slides. Okay. I think that we are okay for today, no?
Totally. Thank you a lot, Pablo.
It was a pleasure.
Great presentation.
We will continue with elliptic curves tomorrow, and also with we have to think what we will do next, but maybe we will jump into polynomials so that we have all the building blocks, and then we can proceed with other applications. But let's talk about that tomorrow. I think it would be best if we just join directly for the second shift at because maybe for the first I'll be a little bit complicated with a conference here in Paris, but let's talk about that. And if you want, we can also start maybe with some one-on-ones for Monday or something like that. So thank you all. Thank you, Pablo, and see you tomorrow later. Bye-bye.
See you guys.
Bye-bye. Enjoy, guys. Enjoy the bootcamp.
Bye. Thank you.